Hello, my name is Stefan Alanis. I'm a PhD student at the Max Planck Institute for Informatics at the University of Tübingen, and I'm going to present our work on how to learn decision trees recurrently through communication. We treat image classification as a communication task between two agents. The blue agent on the left tries to classify an image, but only the red agent, here on the right, has access to it. The blue agent can ask binary questions to obtain information, for instance, whether the object has a certain attribute, and the red agent can answer with yes or no. While iteratively asking more questions, the blue agent can narrow down the image class and solve the problem. By making the questions and answers binary, we can obtain explanations from this communication process, and the blue agent implicitly builds a global decision tree of its decision process. Here are some details on how we achieve this. The red agent, the attribute-based learner, consists of a CNN that predicts binary attributes of the image. The blue agent, the recurrent decision tree, consists mainly of an LSTM that you can see here in yellow. At each time step, the RDT agent predicts which attribute from the vocabulary it wants to request. This is done with Gamba softmax that allows us to draw categorical samples from a distribution. Similarly, on the ABL side, we use a temperature-annealed softmax that binarizes the attributes. The RDT agent communicates the attribute index, and the ABL agent returns yes or no, depending on whether the attribute is present in the image. This information is then fed back into the internal state of the RDT agent, and after it updates its memory, it can now make a better prediction about the class identity of the image. Our whole model is trained end-to-end with a cross-entropy term on the class predictions of the RDT agent. This way, we can even discover learned attributes without any prior knowledge. However, to make the communication process more explainable, we can utilize labeled attribute data with the second loss term that you can see here. In that case, the attributes of the ABL agent will correspond to human understandable concepts. We want our explainable model to stay competitive to non-explainable models such as ResNet. So here we show the classification accuracy of a regular ResNet and one with the additional attribute data on 3 different datasets. When we do not use attribute data, our RDT model maintains the accuracy of ResNet while outperforming competitive decision tree models such as the neural decision forests. We can obtain an even more explainable classifier once we add the attribute data. And again, we do not sacrifice any classification accuracy. Our final classifier can explain its decision in various ways. Apart from looking at the global decision tree, we can inspect which path the images follow through the tree. Here we show 2 images of a bird from the same class. After each binary decision, we see the network's reasoning. In this case, it looks for the white underparts of the birds. And we can also see how this decision affects the class predictions. After following these images a couple of steps through the decision tree, we can observe that their paths diverge when it comes to the decision whether the bird has black wings. The top bird is predicted not to have black wings and is misclassified as a result. These insights allow us to find these critical decisions that can be very useful in analyzing and explaining failure cases. Here's another example of 2 images of birds from the same class. The final predictions are again different, and in this case, the model fails to understand that the female bird of this species does not have a black crown, and instead it only identifies birds with a black crown to fall into that class. We believe that this additional introspection that our model provides can be an important ingredient for classification applications that require more explainable AI. Especially because, in our case, we can achieve this with no cost to the classification accuracy. With that said, I would like to finish my presentation and thank you for your time and attention. For further details, please check out our code in our paper.